So this video is an overview of the beginning sections of Chapter 5 of your textbook. So this will just be sort of the highlights. The details which are important you should review in your textbook. So this covers sections 5.1 through 5.9. So we're going to look at the properties of metals, nonmetals, and semimetals, and some of the reactions that those substances can undergo. So first off, looking at metals. So let's remind ourselves about properties of metals. First off, metals are lustrous. They have that shiny kind of metallic quality, right? They look like metals. Metals are solids, usually at room temperature. So of course you can melt them when you get the temperature higher. The one exception would be mercury, which is a liquid under room temperature conditions. Metals are also malleable and ductile. Malleable is a word that means they can be hammered into sheets. So when you pound on them with an impulsive force, they tend to dent. Ductile means that you can pull the metal into sheets or wires. So if you have, instead of an impulsive force but a shearing force, so you're pulling on it, the metals are going to get thinner in the middle. So that's called ductility or ductile. And the final property of metals is they're good conductors, both of heat and particularly electricity. So we know that those are properties of metals. So what about the properties of nonmetals? So nonmetals have sort of opposite properties. So they'll have almost no lustrous properties. They're not shiny. And in fact, they tend to either be colorless, like nitrogen gas, oxygen gas, or they tend to be really intensely colored, like bromine or iodine. There can be some that are in between. Sulfur is a nice sort of pale yellow color. Phosphorus can be sort of a rust-colored red or a white. So, but they're not shiny. So they can be solids, liquids, or gases at room temperature. So nitrogen, oxygen, fluorine are gases at room temperature. Chlorine is a gas at room temperature. Bromine is a liquid at room temperature. And iodine is a solid at room temperature. So the whole mix is in there. So they are not malleable and ductile. In fact, the solids tend to be brittle. So when you hit them with an impulsive force, they tend to splinter, shatter, or be converted into powder. And they are insulators. So they don't conduct heat very well, and they don't conduct electricity. So semimetals then have properties that are in between. If you look at a semimetal like silicon, you would say that it looks a little bit shiny, so it has a little bit of lustrous property. It's kind of brittle though. When you hit it with a hammer, it tends to powder and splinter. It doesn't conduct heat very well, but it does conduct electricity a little bit under the right circumstances. So semimetals make good semiconductors, which is what the whole electronics industry is built upon. You remember that we can find metals, semimetals, and nonmetals on the periodic table. There's a little quick sketch of a periodic table. You know, if we start up here at this element in this corner, and we draw a little stair-step line all the way down, that divides the metals over here from the nonmetals over here. And then right along this stair-step line, that's where we find the metals that are in between, or the elements that are in between the semimetals. So what this tells you is that metallic character tends to increase as we move to this corner down here of the periodic table. Non-metallic character increases as we go up to this corner. So as you move across a row of the periodic table, elements will become increasingly non-metallic, but their properties vary in a smooth way. Similarly, if you're going down a column of the periodic table, so say you start with carbon and move down to silicon, germanium, tin, and lead, then you see that as we're going down this way, metallic character is increasing. So carbon is not very metallic at all. Silicon is a semiconductor. Germanium is also one of those metalloids. It has in-between properties. And then we get to well-known metals like tin and lead that behave like we expect metals to. So the properties change in a nice regular way as we move from a clear non-metal like carbon to something that is more and more metallic. So metals are divided into classes based on their reactivity. So first, class 1 are the active metals. So they're called active because they tend to be very reactive. These include the group 1 metals, so that's Roman numeral 1A, lithium, sodium, potassium, rubidium, and cesium. And again, metallic character increases as you go down this column of the periodic table, and so they're going to get progressively more reactive. Other active metals include the group 2A metals, so that's the second column of the periodic table, called the alkaline earth metals, and they include metals like calcium, strontium, and barium. So these would be the active metals. So they're active because they will react fairly readily with water and oxygen in the air even. So they can react readily with water and oxygen. So they're very reactive with many substances. Class 2 then are less reactive, and so they're called the less active metals. So these are metals that do not react with water under normal conditions of temperature and pressure, and they include metals like magnesium, aluminum, zinc, and manganese. So even though they don't react with water, they will react with acidic solutions. So they react pretty readily with acids. Class 3 metals are called the structural metals. They react slowly with oxygen. They don't react with water at all. They will react with acids, but you typically have to have a really strong or really concentrated acid for these metals to react very readily with those. And they include metals like chromium, iron, tin, lead, and copper. So metals that we're all familiar with, and partly because they're called structural metals, because most metallic things like building materials, factory manufactured materials that have metallic components are often made from these metals, like tin cans, lead weights, copper contacts, copper wires, iron and steel, all made from these structural metals. And finally, class 4, these metals are basically inert. They're called the coinage metals, and so they don't react very well with much of anything. They will react a little bit, and they include metals that you can find not in an ore form typically, but you can find them sort of in their natural elemental state, not bound to any other compounds. And these include gold, silver, and platinum. So these coinage metals then are really good for making jewelry. So these are different classes of metals based on reactivities. So let's talk a little bit about the kind of reactions that metals can do. And one thing we know about metals is that they tend to have a low average valence electron energy, which of course goes along with electronegativity, and this means that they do not hold on very tightly to their valence electrons. So a lot of their chemistry is dominated by losing electrons to other kinds of elements. So they tend to lose electrons in chemical reactions to form cations. And you'll remember that cations are things with positive charges. So they're going to form ions typically, and they're going to lose electrons. That's a dominant form for their chemistry. So let's look at some of those, and we'll see some patterns. So first we're going to look at the group 1A metals. So these are the alkali metals. And let's look at sodium. So sodium has the electron configuration 1s2, 2s2, 2p, 2p6, 3s1. So this first part of the electron configuration, you'll remember, is just the electron configuration of neon. So because it holds onto this electron right here very weakly in this third shell, it's fairly easy to remove that electron. So we're going to remove an electron, and so we're going to end up with an electron configuration that is the same as neon. So now we've got a complete inner shell. We've got this noble gas configuration. We talk about how typically stable that is. So now we've got a 3s0, so there's no electrons. So we will typically lose one electron then to form the sodium cation. So it will have a +1 charge. That's the common charge formed by a sodium cation. Well, why wouldn't it form a +2 charged ion? Well, if you want to take 2 electrons away from sodium, then you're going to have to dig into this inner core, right? You're going to have to dig into the n=2 shell in here and take away one of these electrons to remove a second electron from sodium. And the n=2 shell we know is much closer to that nuclear charge, and so those electrons are going to take a lot more energy to remove. So we remove 1 electron for sodium, and then we stop. So sodium will readily lose 1 electron, but not more than that. And we'll figure out that most of the group 1A metals do the same thing because they have this outer S1 electron configuration. Similarly, we will determine that metals like calcium that have a 4s2 configuration, so this is one of our group 2 metals, so one of the alkaline earth metals, that this element, calcium, will tend to readily lose 2 electrons to form a 2+ charged ion. And then it will have the same electron configuration as argon, B4s0, because we've taken those 2 electrons out of the 4s orbital. So group 2A metals tend to form +2 charged cations. Why not +1? Well, they could form a +1, but you can get to this stable noble gas configuration by losing 2 electrons. And we've learned that atoms will tend to gain or lose electrons to adopt the electron configuration of the nearest noble gas. So you'll notice that there is a pattern then for metals. So for main group metals, it turns out that the Roman numeral group number equals the maximum cation charge. So metals form cations. What's going to be the maximum charge on typical charge formed by a particular element? It's going to be the group number. So for example, if we look at aluminum, aluminum is in group 3A, and so knowing that, we can predict that aluminum is probably going to form a +3 charged cation when it makes a cation. If we look at some other metals, so say we look at lead, lead is in group 4A. So that means that lead can form at most a +4 charged cation. It turns out that lead also forms a +2 charged cation. But both of these are possible, and so the maximum one that's available, that's why I put max here, the maximum charge that an element will typically form is their group number. So that's for main group metals, okay? So it has to be main group, not transition, and we're talking about metals, not nonmetals. So what about those transition metals? So in order of filling, iron would have this electron configuration, argon 4s2 3d6. So if it's going to lose some electrons, it can lose those electrons out of either the 4s shell or the 3d shell. We will probably remove electrons from the 4s shell first because the N=4 shell on average is further away from the nucleus. So these electrons will be easier to remove. So you might guess that we could remove 2 electrons and then we could form a iron 2+ cation, which would have 4s0 3d6 as its outer electron configuration. We could also lose 3 electrons to make an iron 3+ cation, which would be 4s0 3d5. You'll remember that having a half-filled subshell confers a little bit of special stability. So maybe there would be some impetus for iron to go ahead and give away 3 electrons, 2 from the S shell and 1 from the D shell to make an iron +3. So both of these cations exist for iron. And in fact, there's some other ones as well. So we can continue to remove some electrons out of the 3D orbital. But these are the most common. So other transition metals will form different common ions. So zinc only ever forms a +2 charged ion. Silver only ever forms a +1 charged cation. Copper will typically form either a +1 or a +2 charged cation. And again, we're going to try to remove those electrons from the outermost shell first, working our way in, taking away either S or D electrons. So the S electrons first, and then the D electrons typically. So transition metals are a little bit more complicated then in that they have multiple charges that are common for those ions, and we can't just use the group number all the time to tell us that. So let's think a little bit more about the nonmetals. So nonmetals, one property that we know about nonmetals is they tend to have high average valence electron energy and electronegativity, meaning that they hold on very tightly to electrons in their valence shell. So because of that, they're going to tend not to lose electrons, and since they want to get to a complete shell, they are much more likely to gain electrons to adopt a noble gas configuration. And an electron that might be in their valence shell will tend to be stabilized by being in that tightly held valence shell. So the chemistry of nonmetals is often dominated by them taking electrons from other species to complete their valence shells. And we've already seen how most nonmetals, when they bond with each other, will tend to share electrons and form a covalent bond. So when nonmetals react with metals, however, we've got one atom that's really pulling on the electrons, the nonmetal, and one atom that has a really weak hold on the electrons. So what ends up happening is that we end up completely transferring an electron, essentially completely transferring an electron from the metal to the nonmetal to produce an ionic compound. So let's think about how nonmetals might form ions. And so we're going to look first at the halogens. And so this group is group 7A, so fluorine, chlorine, bromine, and iodine. And these elements will tend to gain 1 electron. So let's look at the electron configuration, say, for chlorine. So chlorine's electron configuration is neon 3s2 3p5. So if we were to add an extra electron into this, we would make an electron configuration that's neon 3s2 3p6. So we've now completely filled the 3p orbitals with 6 electrons, and we now have the same electron configuration as argon, a noble gas. And so that's a particularly stable arrangement, as we've seen with noble gases, because we've completed that shell. And so we will have made a Cl- chloride. So when we form anions, they often will end in IDE for the name. So this is chloride. So we've made chloride. And chloride, bromide, and iodide collectively are known as the halides. So halogen is the element. Typically they're diatomic elements. Not typically, they always are diatomic elements. And when we formed anions with them, we've made halides. So by picking up 1 electron, they make a halide. So let's look at the next group, group 6A. We're moving now right to left on the periodic table. So group 6A, this group has a name. It's called the chalcogens, which literally means chalk formers, because they often bind with metals to make sort of chalky ionic compounds, things like magnesium oxide, calcium oxide. So a lot of oxides used to be called calx, metal calx, referred to the oxide coating that was formed on the surface of certain metals, our reactive metals. So this group includes oxygen and sulfur. And so oxygen has an electron configuration, helium, 2s2, 2p4. And so we see that we can complete the valence shell on oxygen if it picks up 2 electrons. So an oxygen atom will typically pick up 2 electrons to get the electron configuration 2s2, 2p6. And so that's going to make O2- that we call oxide. Again, the IDE ending since we've got an anion. So we've picked up 2 electrons for the chalcogens, and then you might guess that the next group that we find, group 5A, these are called the pnictogens, and they include nitrogen and phosphorus. So nitrogen has the electron configuration helium, 2s2, 2p3, and so we see that if it picks up 3 more electrons, then it can complete its valence shell and have the same valence shell as neon. And with 3 extra electrons, it will become N3-, also known as nitride. So again, the IDE ending is telling us that this is an anion. So nitride with 3 negative charges completes its valence shell. So you'll notice that there's a pattern there as we move from left to right across the periodic table, so that the noble gases here don't tend to gain or lose any electrons, so they don't tend to form any kind of ion. Then our first group here, the halogens, they're going to tend to form a -1 charge. Then the chalcogens next door, they're going to tend to form a -2 charge. And the pnictogens next to those guys are going to tend to form a -3 charge. Now again, we're just talking about the nonmetals. The metals we know will tend to lose electrons. So there are metals down here that will tend to lose electrons. In between, the semimetals tend not to very easily gain or lose electrons. They tend to have to share electrons to complete their valence shells. So there's a little bit about the chemistry of nonmetals. Let's look at one special case, and that special case is hydrogen. Now hydrogen, as we know, has a 1s1 configuration. So you might guess, like some of the other s1 configurations that we've seen, that hydrogen could lose 1 electron and become H+. That would be 1s0, so an atom that actually has no electrons. So it's simply a bare proton. So sometimes we refer to H+ as the proton. Now protons don't typically exist by themselves in nature, so they will tend to attach themselves to the nearest bunch of electron density they can find, and that is often an oxygen atom, because oxygen is very prevalent in our environment. So hydrogen can do that, but hydrogen can also complete its valence shell by gaining an electron. So like the halogens, hydrogen atom could gain 1 electron and form an H-1 anion with a 1s2 electron configuration, which is the same as the electron configuration of helium, a filled shell. And so when we do that, we form a species called a hydride. So H-1 is a hydride. So hydrogen can actually take electrons from other atoms that have lower electronegativities. So when hydrogen reacts with a metal, it will tend to take an electron away from the metal and become the hydride anion. So let's think about some reactions that could take place then between metals and nonmetals. But before we do that, we need to talk about a very important idea. And so that's predicting the formulas of ionic compounds. So ionic compounds, again, are sometimes called salts, and they're made from the combination of a cation and an anion. So we need something with positive charge, we need something with a negative charge. They'll stick together because plus likes minus, and then we've made an ionic compound that forms something called an ionic bond. So an important characteristic of ionic compounds is that the formula must have electrical neutrality. So in nature, plus charges and minus charges like to stick together. So locally we could have a negative charge, but somewhere nearby there's going to be a positive charge to offset that. So in ionic compounds, we will always maintain electrical neutrality, which means a net charge of 0. So for every positive charge, we have to have an offsetting negative charge. So let's think about an ionic compound that might be formed between these two ions, between calcium, 2+, and carbonate. Carbonate's a polyatomic ion. The oxygens are covalently connected to this carbon atom, and overall this molecule has 2 extra negative charges. So we could make an ionic compound with these 2 ions. So we want to do so that we have electrical neutrality. So for every positive charge, we need to offset it with a negative charge. So right now this calcium has 2 plus charges, and over here this carbonate has -2 charges, a total -2 charge. So we can combine 1 calcium for every 1 carbonate and write down a formula that looks like this, CaCO3. So So that tells us for every one calcium we have to have one carbonate. So for one calcium we get one carbonate, and then we have electrical neutrality. So another example, let's imagine that we have a calcium that's forming a compound with chlorine, a chloride. Okay, so now we've got chloride ions, we've got calcium ions. So you see that the calcium right now, we've got a +2 total charge for this cation, and we've got a -1 total charge for the anion. So that's not enough to offset the calcium. So what we're going to have to do is have a second chloride anion right here, and then we can pair these two up with the calcium to make a compound with maybe one chloride stuck on either side of the calcium here, and we're going to make a formula that is now electrically neutral, CaCl2. So we must have charge balance. Let me show you a quick way of figuring out the charge balanced formula for a ionic compound. So I call this crossing the charges. So if we go back to this last example, calcium chloride, then we see that there's a +2 charge here and a -1 charge here. So what I'm going to do is I'm going to take the charge here, and without the sign, that's going to become the subscript on the chloride. And then I'm going to take this charge here, and I'm going to cross it over. That's why I call it crossing the charges. And without the sign, that's going to become the subscript on the calcium. So we get Ca, and that's going to be a 1 down here. But since it's a 1, we're going to not write it. Okay? So if we don't have something written there, it's assumed to be 1. Then we have Cl, and our subscript, we cross the charge, the +2 comes down without the sign and is just 2 for chloride. Now, if you go back to our example that involved calcium and carbonate, and we did this process of crossing the charges, then what you would predict is that we have Ca2, and then we would have to have 2 carbonates. But what we always do is we write it in terms of the smallest whole number ratio. So you could think of dividing both of these coefficients here through by 2, and then we get the formula that has the smallest whole number ratio of the ions, CaCO3. So that would be the right formula. Now let's do something a bit more complicated. Let's look at Fe3+ forming a compound with carbonate, CO3 2-. And let's think about what the formula is going to be for that has charge balance. So I can't do one of each because then I'd have too many positive charges. If I do 2 carbonates, then I would have too many negative charges. But crossing the charge will help me keep everything correct. So the 3 is going to become the subscript on the carbonate, and the 2 is going to become the subscript on the iron. So I end up with Fe2, then in parentheses, because those guys have to stay together, I've got 3 carbonates. So this will give me a charge balance formula. Fe2CO3 would be the formula for the compound formed by iron 3+ and carbonate. And so that works for any ionic compound to make sure that you have charge balance. Now we're going to look at some reactions that produce ionic compounds. So let's think about the reaction between sodium, which has 1 valence electron, and chlorine, which has 7 valence electrons. Now what we know is that sodium has a low average valence electron energy, so it doesn't hold on very tightly to its outer electron, whereas chloride has a relatively high AVEE, and so it's going to tend to pull this electron towards itself. So we know that metals are dominated by their tendency to give up electrons, so what we're going to do is lose an electron, and we're going to form the sodium cation, and then we're going to form a chloride anion. We've now completed the octet, completed the valence shell of chloride with a negative charge. And so now this plus likes minus gives us a force between these two guys, and they're going to stick together. So that's what we imagine happening, and in terms of a balanced equation we would say that sodium metal reacts with chlorine gas to produce NaCl as our charged balance equation, right? So we have Na plus Cl minus, we cross the charges, we get NaCl. And that's ordinary table salt. And it's a solid at room temperature and pressure. And in order to balance this equation, we would need to put a 2 right here and a 2 in front of the sodium. So that's the reaction then between elemental sodium and elemental chlorine to form another compound, sodium chloride. And again, it's dominated by this behavior of metals to lose electrons and nonmetals. Another example, we can look at the reaction between potassium, solid, and hydrogen gas. Now what we know about the electronegativities of these two guys, which are related to the AVEEs, the electronegativity of potassium is 0.73, and the electronegativity of hydrogen is 2.30. So in the tug of war for electrons, hydrogen wins. It's a lot stronger. And so what's going to happen is hydrogen's going to actually take that electron and form the hydride. So we're going to take the electron, form a hydride. We're going to form a potassium cation. Potassium forms a positive charged cation. We cross our charges to get the formula, and so we get KH, potassium hydride, as the formula for that. And potassium hydride exists as a solid. And again, to balance this chemical reaction, we would need to put a 2 in front of the potassium hydride and a 2 over here in front of the potassium. There's another example of a reaction that could take place between a metal and a nonmetal, like hydrogen. Before we leave nonmetals altogether, we should talk about one special thing that oxygen can do. Now, even though I told you that oxygen will tend to pick up 2 electrons to complete its valence shell and form most commonly the oxide anion, and we often see that happening in reactions between metals and oxygen in the air. So when iron rusts, for example, iron metal rusts, it will tend to combine with oxygen. And if this happens slowly, the electrons will gradually be transferred to the oxygen atom, and we will make iron oxide. So we start off with an iron 3 cation, and from giving 3 electrons away to some oxygen atoms. And so oxygen is going to form an oxide, so we cross our charges, we get Fe2O3, and that's going to be a solid. Rust is a solid. And again, to balance this equation, we'll have to do a little bit more work here. We need 2 irons, and then we're going to need 3 oxygens over here, so one way to do that is have 3/2 of a mole of oxygen. 3/2 mole, right? So 3/2 times 2 gives me 3. Or if you wanted to balance this reaction in terms of whole numbers, then you would need 6 irons. So if you wanted to balance this reaction in terms of whole numbers, we would need 4 irons, 3 oxygens, and we'd be making 2 iron oxides. So that shows the formation of an oxide. Now, some metals react so quickly with oxygen. So for example, sodium reacts very quickly with oxygen, so that oxygen does not have enough time for this molecule O2 to break apart by the time sodium has given it all of its electrons. And so we end up forming a compound that has this formula, Na2O2. So we could think of that as being formed from the sodium cation and the O2 2- polyatomic cation. So this guy right here is called peroxide, and it would have a Lewis dot structure like this, a single bond between the oxygens. So it would have picked up 1 extra electron, and it'll have an overall 2- charge. So we haven't had enough time to break the double bond between the oxygens. We've only partially broken it by giving it 2 electrons from a couple of sodium atoms, and then we formed this structure, Na2O2. And if we're writing that in terms of the smallest whole numbers, we would write that as NaO, and people will know that as peroxide, but it's probably better because the O2s actually have to stay together that we write it this way. So we have to keep the O2s together in this compound. And so this is a better representation for sodium peroxide. Now, peroxides tend to be pretty reactive things. But there's one that's even more reactive, and that's the superoxide. So in metals that are even more reactive than sodium, we could imagine doing the same reaction, say between potassium, solid, and oxygen gas. We end up forming a compound with this formula, KO2 solid. So this is known experimentally, right? We wouldn't have predicted this because we would have figured that oxygen makes this oxide. But if we think about what this is, we've got K. We know that potassium always forms a +1 charged cation. So O2 then with charge balance would have to form a -1 charged anion. Then we have charge balance. So again, this is a polyatomic ion, O2, but we've got an excess -1 charge on it. And this species is called superoxide. And superoxides are very reactive. In fact, if you have a lot of potassium superoxide coating on a chunk of potassium because it's been sitting out in the air, then as you begin to cut potassium metal, you're going to bring that KO2 in contact with the bare potassium below it, and that's going to cause a reaction. And it's going to cause a potassium superoxide to form regular old potassium oxide, and in the process, it's going to generate a lot of heat, enough heat to melt the potassium right where you're cutting, and that's going to react with water in the air fairly readily, make some hydrogen gas, and the whole mess could explode. And it's really fairly dangerous. But so we worry about peroxides and forming peroxides and superoxides because they're often very reactive. So the oxygen would really like to pick up some more electrons. It just didn't get the chance before it ran out of metal to work with. So those are oxides, peroxides, and superoxides, and they drive home the point that even though we know something about common ions that get formed, we really have to do experimental work to verify that there aren't other kinds of things that could happen. So we might have predicted that the reaction between potassium and oxygen would give us plain old potassium oxide, not predicting that this potassium superoxide could form or that sodium peroxide could form.